Okay, come. Welcome to our penultimate class, right? So Wednesday is our 8th class. We'll finish our summer together. On Friday, the same time in the morning, the 9th lecture, so to speak, is actually an introduction to applied digital intelligence track, right? You have to look out for the other 3 sessions like that, except I'm not sure where that will be. So that's introduction to sustainable development track, health and well-being, right? Smart city and inclusive society. Those should be coming up. Either some may have already taken place, I'm not quite sure, but certainly around the next week or so. Okay. Now next week we have an AI sort of like literacy boot camp. Let me give you a few words of that, just to give you a heads up. The idea here is that AI is now going to become ubiquitous, right? Ubiquitous. And you have to be prepared for it. Now, there are 2 meanings of the word prepare. And in fact, this is something that we're going to have the conversation with Thailand's leading academics and leading thinker on Friday afternoon, this Friday afternoon, right? But it gives you a perspective. There are 2 ways of thinking about preparedness. One is you have to brace for impact. You know, it's sort of like this big wave is coming, you're on a small boat, so brace for impact. That's what this means, okay? So that's preparedness, because it's going to shake the whole boat and so forth. The other preparedness is this. When the environment changes, it's a big opportunity. So how are you going to make an early lead? When everybody's sort of like panicking with what's happening, right? Who's going to be able to take advantage of the change? That's the second meaning of preparedness. That's sort of like acting, right? So we want both meaning of preparedness for the future of, digital AI-driven world. Okay. In fact, even the education system, the university, our faculties, we have to do that preparedness as well, right? What's going to happen when, let's say, you used to be able to say, grade students on how well they can elaborate ideas into an essay, but no matter how you did it, chances are for a short, concise essay answer to anything, ChatGPT will probably, write up something fairly neat, right? Something that has a point A, B, C, and so forth. Now, you learn about the limitation of large language model like ChatGPT later, of course, but at least that's something that's going to be a disruption. Okay, that's a disruption. And so anyway, so next week is all about getting you guys to understand what's happening to your world, and so that everybody has basic foundation of AI, right? And how it's going to impact you, how you're going to impact it or benefit from it. And some of the objective, I think Professor Warasat was thinking, was that in the past, Basai students have been technology shy a little bit too much. So maybe opt for, doesn't go for applied digital intelligence because thinks it's too difficult. And he just want to say, well, it's not that difficult. My feeling is ambivalent. I don't really think that all of you or many of you or even majority of you should pursue applied digital intelligence. On the other hand, you'll never get away from it. Like I said, the 3 tracks, sustainable development, smart cities, inclusive city, health and well-being, these are sort of like problem looking for solution. And chances are some of the solutions will be found in the world of applied digital intelligence. Likewise, applied digital intelligence is problems looking for, solution looking for problems. And chances are in your generation, the key problems are sustainable development, health and well-being, smart cities, and inclusive society, right? So it's a little bit like a different perspective. Okay. I mean, I'd be completely happy that, everybody goes sort of like quarter, 25% in each. I think that'd be kind of nice. Okay. So one is a frontier in pushing in the applied intelligence and looking to apply. right? And maybe application is in the other three area. The other three would be looking for solution, and maybe the solution is within applied digital intelligence, okay? But solution maybe not, maybe in the policy space, maybe in marketing, whatever. Yeah. Right. I wrote this kind of summary. I really want you to write this yourself, but I couldn't help it. But I just thought I write the summary and give it to you. So last week we finished up linear algebra, right? We start with linear algebra as an extension, a multivariate extension of the equation ax equal to b, right? Except instead of 1x, we have 10x, 20x, 100x, 1000x, 10,000x. Okay. Instead of solving for x is equal to b divided by a, we say, well, x, the whole vector, is equal to the inverse matrix a, right? Right? Times right hand side of b. And that's how you solve for it. Okay. I mentioned briefly that in real life, computationally, maybe you don't actually get to the whole inverse at once, sort of like chip away at it. And maybe I'll give you this Jordan code to play with. That's the concept. Right. Now, Friday, I flipped the story around. Instead of saying, given ax equal to b, and there's a lot of x, solve for x, I start by saying, well, how about this? How about look at the a itself as a constant? What does it do to x? What does a do to x? Any x. Okay? And the concept here is two things possibly happen: rotation, extension. Right? The rotation just move things around in a hypersphere or circle. And extension means you don't change the direction, it's still finding the same way, but maybe a little bit further, a little bit or somehow, or maybe go the other way. Then I show you that for any vector, if the matrix happens to look like nothing but diagonal of some number, it's just gonna create an extension by that multiplication number, right? So if your matrix is 7 on the diagonals and everything else 0, well, what it's gonna do is gonna lengthen the vector, it's multiplied by 7. Just like you will multiply 4 vectors by 7. But that's not boring. That's not interesting. That's boring, right? But then the matrix of diagonal 7 will just make every vector bigger by 7. Now I flip the question around and say, well, what if I have a matrix, right? A matrix that doesn't have this structure. It's a whole bunch of numbers. Well, is there a direction x in which when you multiply a to it, it keeps going in the same direction? And that's where we get to the concept of Eigen system, right? And somebody's asking me after class about why Eigen system is one of the way of analyzing matrix. There are many other ways. And when I was studying, as a student of matrix theory, I learned about this, I learned about how you decomposition, all kind of decomposition analysis. The reason I picked eigenvector or eigensystem decomposition to be due is because in my career, and I think in your future, you will see that these are the ones that you will run into so often. Okay? And of course, I gave you 3 examples, right? One is how Grade and Page use this mathematics to optimize their search result, okay, by ranking in relative importance. 2, this is also how social network analysis is done today. Okay? And sort of like in between, I stuck in an example that we had about because I was the first one here was to find kind of significant financial institution by looking at network of borrowing between banks. Right? So network of borrowing between banks, network of friends on Facebook, network of links, hyperlinks, right, on internet. These are all graphs. And this is a powerful way of analyzing graphs. Okay. So we got to that, and we kind of finished with that on Friday. Now, so let's go back to this. AX is equal to B. Okay? AX is equal to B. 3x is equal to 13. Okay? Matrix or linear algebra is about extending in dimension. Meaning, instead of just have one x, you have 1,000x. Right? Calculus doesn't address that again. Okay? Fundamentally, what calculus does is it deals with the case where it's not just ax. What if it's ax squared? Okay? So basically, all the nonlinear stuff. Okay? Now, all this have been around before calculus. It's called parabola or conic section, x squared, x cubed. Okay? The difference is this. Calculus focused on one aspect initially, the rate of change. When you have 3x equal to 13, every time you increase x by 1 unit, the right-hand side goes up by 3. You can actually read it, right? So x goes up by 1 unit, the right-hand side goes up by 3. Now, if you have 3x squared plus 5x cubed minus log of x, what happens when you increase 1 unit of x? You can't switch the coefficient, right? You can't switch the coefficient. Now, here's the deal. You come around, you come to two options. You come to two options in life. One way is, well, how about this? How about I move x a little bit and I take the measurement. So x equal 1, get some value. X equal 2, get some value. Well, that suddenly is a change, right? So you divide by the difference. We'll divide the difference by 1. So that's what the change is, the rate of change. Okay? But that, of course, is kind of like rough, right? You have to always increase x by some finite unit, from 3 to 5, to 3 to 1, or 3 to 3.1. Fundamentally, by the way, that's how engineers would often have to do it in real life. Now, would it be nice if you actually can calculate instantaneous rate of change? Okay. So the perfect example would be if you're driving at 50 miles an hour, right? Every minute you add to that, you get 50 times 1 over 60, right? So it's simple. So you always get that speed, right? Because the speed is constant. The reason is because the speed is constant, the distance covered is easy to calculate. If you know the distance, you can ask for average speed. Now, when you drive in the car, you actually have what's called speedometer, right? So that gives you a quote unquote instantaneous speed. Technically, it's not, okay, but just pretend that you have a perfect machine that measures the speed of your wheel. But that's what calculus tries to do. So instead of saying that I can only calculate distance for a car that travels at a constant speed, or I can calculate the speed on only the average speed over a distance, over an amount of time. I can get something more precise, more instantaneous. That's what calculus does. Okay? So it's an extension to 3x equal to 13 because you're not just doing that for this thing. You're doing it for 3x plus x cubed minus log x equal to 75. Right? What happens? That is what calculus does. So why do I tell you this? Well, in a calculus class, you often learn calculus. Just like linear algebra, you go there and you learn calculus. But the bad side, you learn the perspective. Why does calculus enter in your life? Why does linear algebra enter in your life? These are perspective questions. These are perspective thinking. These are intellectual development. These are things that is expected of part-time students. Right? Now, let's get to the fun. Let's get going. However, before we get to calculus, I'm going to have to take say 15 minutes detour. Okay, that 15 minutes detour has to do with what's called combinatorics. Again, as a mean to an end, it serves very little purpose to get to calculus. This is one of those key chapters that I said, discrete machinery, discrete some kind of thing. But it turns out combinatorics is also one of those things that will be very important part of your logical analytical thinking. Yeah. So for that, I'm just gonna need a blackboard. Conveniently, this is all black. Literally. Okay. So I'm actually gonna write into this. Oops. Where's my number lock 6.1. Intro to combinatorics and Pascal triangle. By the way, this is what I use ChatGPT and Google for. I try to get a consensus of what general population likes for things that are not black and white. Okay? For example, is it Pascal triangle or Pascal's triangle? Okay? They're both correct. Okay? But if I'm going to write a text, I would like to be in the majority. So sometimes what I would do literally is just put this in a quote and search in Google and count, one may have 100,000 hits, the other one has 7 million. So, okay, people tend to use that. Okay, so that's what I would do. Likewise, ChatGPT is a very good way to get a sort of like consensus expression on certain things, but it's not information source per se. Okay, so don't rely on that. So, I would do that. Okay, so let's do this. You guys have done well, you've done this enough, right? So x plus 1 and x minus 2, right? Well, actually, you usually do the opposite, right? You get the multiplication, you factor it out, okay? By the way, that's one of those things where Mathematica can do and you can't get any general language, Python, or it doesn't do it because it's analytical. But if you say factor, there's a function called factor in Mathematica. So if you had this in high school, that's very bad. It's just an algorithm, basically. Okay, now, so you know how to multiply this. What I'm going to do is I'm going to make the term the same. So it becomes a power. So if I don't do this, right? But I do this, say x plus 1, right? This is the same thing as writing to the power 2, correct? To the power 2. Okay, so let's think about that. Okay? Now, normally in that algebra class, the first term is something with x, the second term is something not with x, right? So maybe this could be something like 2x plus 1 or something. Okay, I'm gonna make it more general. I'm gonna say a plus b to the power n. Okay, a plus b to the power n. In particular, how about a plus b to the power? Let's do it to the power 4. Okay, power 4, right? So I'm gonna write it out. Okay, very good. A plus b, a plus b. What's that gonna equal to? Well, you can certainly multiply it all out, right? Multiply it all out. But you remember this thing about front, back, front, right? That's how you work the combination. Okay? So I have 4 students. And how many combinations can I make? Okay? By pairing you at a time. Okay? So 4 students, how many pairing can I get? So this one 2, that 2. this two, this two, this two, and that two. That's it, right? Right? Likewise, how many ways can you get front? There's only one, right? So in other words, there's only, okay, front, I'm going to use F, okay, front, okay, and that will give you one term with a square, sorry, a 4, okay, right? So let me put that in a bracket. You see why in a minute. Okay, now how about front, back? Okay, right? What else? Front, back, front. Right? Front, back, front, and back, front. How many ways is that? That gives me exactly 4 terms with a to the power, what? 3 of them, right? Times b. Okay. Likewise, if I repeat this example, you can see that, let's go back to, it's very symmetric. So you can see that at some point in the back end, I'm going to have, oops. Okay. Let's just flip this thing around. Back, front. Back, front, back. Back, front, back. Front, back. Okay. So that's going to also be 4 terms with a times b to the power 3. Okay. Now in the middle, it's going to be a little bit more colorful. So let's try that. FFB, right? What else? FB, right? BF, okay? Right? Now, how about FBF, okay? BF, and BBFF. Anybody can think of more? I don't think you can, right? So that will give you exactly 6 terms with a to the power 2, b to the power 2, right? Let's see the mouse. Oops. And finally, I get BB. And that gives you 1 term with b to the power 4. Okay? So remember this word. This word is called 14641. Right? 14641. Now, if I were to do this in a general case, am I going to be writing all this down? No, that's going to be terrible, right? It's going to be terrible. Okay? Well, I'm going to turn this around. Okay? So I'm not going to think of this for a while. I'm going to think of something else. 6.2. Okay? What happened when I get the number 14641? Those are different cases, but they share one thing in common. The number of A's and number of B's. That's why I put them together, right? So in this line, there are 4A. In this line, there's 3A and 1B, okay? By using front, back, front, and so forth, right?
So basically, one note something like 6 is the number of ways I can pick out two A's. Now let's use 4. 4 is a number of ways that I can pick out 3 A's out of 4. Right? Out of 4, you know, 4 spots. So let me write it this way. So number of ways I can, okay, pick 4 items, A or B, with 3 of A. Okay? Right? Okay? So I'm going to call this number of way. I'm going to change it. I'm going to call it. I have 4 chooses 3. Okay? This is my shorthand. I don't want to write this long sentence. Okay? This is 4 choose 3. Okay? It's 4 choose 3. Okay? Likewise, this is what? This is 4 choose 2. This is 4 choose 1. This is 4 choose 0. Right? So, in other words, i.e., okay, what I have above, hence, oops, okay, I have 1, 4 chooses, how many? 4, right? Right? Because I have 4 spots, I'm going to pick all A's, right? Likewise, I can keep writing. Okay? So 4 is equal to 4 chooses 3. Okay? So 3 A's. 2, 1, 0. Okay. When I was learning this, my probability, well, you see why it enters in probability later. Okay. Now, I don't recommend you play cards for amusement. It's a bad habit, just like any kind of games, sort of like get you addicted, I guess. But this is what playing cards teach you, combinatorials. Okay. So, right? Okay. So you agree with me? Can you agree with me with this? Yeah, this is very basic, right? I work everything out in detail, so you can't really argue with me there. Okay. There's only one way you can pick 4 numbers for 4 position, and then just take only one A, all A's or all B's. Okay. How is that calculated? How's that calculated? Okay. So let's think of this choosing thing. This choosing thing. What is this choosing function? Okay. Well, the way you think about it is like a seat. Okay. Look, there are 5 empty spots right now. 5 empty spots. Now, for the calculus application, you're only choosing 1 to, up to n. Right? But in general, this works everywhere on Earth. Okay? You have 5 spots. Okay, 5 spots. Okay? How can you fill them? With two. In other words, I have A, right? I can put A or I can put nothing. Okay, forget A and B, just say A or nothing. How many configurations have I got? Well, I can put A. That's 5, choose 5. I can put nothing. That's 5, choose 0. Okay, now let's focus on 5, choose 3. 5, choose 3. Okay, 5, choose 3. How many configurations? Well, I think I have a whole bunch. I have a whole bunch of A's in my hand, up to 5 A's, right? I'm gonna assign 3 of them. So how many possible ways have I got for the first A? Where can A sit? 5 ways. Right? Once you got the first A sat down, where's the second A gonna sit? Can it sit on the first guy? Did you sit on the same lap? No, can't sit on the lap of your friend. So how many choices you got? 4. Right? How many, what about the third one? That's my last one, 3. So basically 5 choose 3 is calculated by 5 times 4 times 3. Right? 5 times 3. Now, 5 times 4 times 3 is a little bit. So let's focus on, I'm going to make number bigger so you don't get hung up. 7 chooses 5. Okay? So how many ways? That's equal to, now, 7 times 5. Let's make 7 choose 3 because I don't want to write too much. 7 choose 3. 7 times 6 times 5, right? But let's put X. 6, 5. That's equal to how many? Okay, right. So 7 way, the first A can sit. 6 way, the second A can sit. Okay. Now, this number is, let's say, difficult, or it's a function. How can you make a function? Let's say I give you 1 power. Your power to calculate factorial. So you can multiply 7 by 6 by 5 by 4 by 3 by 2 by 1. You can't stop until you get to 1. So how do you get this? How do you get this? Well, if you think about it, let me just give you the answer. Okay. Let's give you the answer. Okay, the answer. Okay. What if I give you 7 factorial is equal to 7 times 6 times 5 times 4 times, right? Okay. Right. Now let me give you another one. Okay. 5 factorial is equal to 5, 4, 3, 2, 1. Okay. 5, 4, 3, 2, 1. So how many? So in other words, this thing, okay, this thing, but by the way, you should be making this note down, but beware that what I just gave you is wrong. But write it down first. Write it down first, but don't save it and send it to your mom. That'll be wrong. Okay. So what it looks like is that I get 210, right? Different ways. Different ways, okay? So that's equal to 7 factorial divided by 5 factorial is equal to 210. Is that perfect? That's how many ways I can set this down, right? Right? Okay. Now, okay, these are how many ways I can put in a row of 7 and put 3 A's. However, if I don't care about identity of A, does it matter if the first one is here, the second one is here, the third one is there? Or the first one is here, the second one here, the third one is there? Does it matter? Does it matter? So what happened is, this is what I do. I take the 3 seeds that has A, I bring it out, set it aside. So there's a seed of 3, right? And how many configurations do you have? So that would be the first guy has 3 places to sit, second guy has 2 places to sit, the third guy has 1 place to sit. So in other words, there's number 6, right? Okay, so how many ways can I see 3 students in 7 chairs? Okay, so 210 ways. But now I don't care about individual students. Okay, because you mean nothing to me. You're just a student, right? You're not my child, right? So in that case, doesn't matter if you sit in that order, or you, or you, right? So there's another factor of 6 that doesn't matter to me. So I have to divide that out, right? So this thing is incomplete. It should be something like 7 times 5 times 3 divided by what? 3 times 2 times 1. Okay, so what's that equal to? Now I divide everything by 6. So I get 35. Okay, so now what I do is I calculate 7. Oh, sorry. I'm sorry, guys. I was being sloppy here. 3, right? 7 choose. Oh, no, that's fine. That's fine. 7 choose 3. So 3 people sit. Yeah. That's so 5, 4, 3, and then there's 3 factorial. And that's correct. Okay. So what I want to do is 3 factorial. 3 times 2 times 1. Okay. It's this line that's wrong. Okay. So what I want to do is it's not only 7 divided by 5 factorial, it's divided by 5 factorial times 3 factorial. Okay, now you get the right answer. Okay. Finally, last step. Notice this problem specifies 7 and 3. So 5 enters. Well, actually, to write it as a formula, when you get the number 5, 7 minus 7 minus 3. Wait a minute, it should be 4. Okay, it should be 7 minus 3. So that's 4. Oh, okay. What am I doing wrong? Oh, it should be this class. Sorry. Okay, yeah. So this is 4, 3, 2, 1, and then so that's this. It's my mistake, sorry. Okay. Now, if you did this on Mathematica, you wouldn't make mistake because it's not by hand. Check. So the formula here is 7 minus 3. Thanks, guys. Good eyes. Okay. So in other words, if I'm going to have, okay, n choose k, n choose k, right? What am I going to have? I'm going to have n factorial divide by what? Right? By n minus k factorial. Okay. But because amongst the k, I don't really care either. So I'm going to divide another k factorial. Right? Now, to make sure that you get the sequence right, it's going to be like this. Now, so if you go to any kind of Mathematica, so let's new. Okay. So if I have 7, what is it? 7 choose 3, right? 7 choose 3. So 7 factorial, the whole thing divide by, okay? Divide by, oh, let me do this. Let me go n factorial divide by n minus k factorial, and then k factorial. Okay. Now, I'm going to give you another thing I haven't given you before. This function is called replace. It's so used so often. What I'm going to do is this, slash dot. That's replace. Okay, it's if you go to the word replace, you can use this function as well. So let's say replace this. Okay, replace this. Now, this is the rule. If I see n, I point to 7. If I see k, I point to, what's it, 3? Oh. So, why am I not writing something correct? Where's the help? Replace. Oh, replace all. Okay, that's all. Yeah. Obviously, if it's replaced, it's looking for this. Replace all, I mean, these are the rule. Okay. In fact, you don't need to, you can put in the brackets, fine. Okay. Now, this thing is used so often, this kind of replace is used so often, so they create a shortcut for it like this. Okay. So this is a shortcut for replace. Again, you don't have to care. You can use the whole thing, but if you look at my code, sometimes I would write like this. It saves me a lot of typing. Okay. Right. Now, so obviously, Mathematica is going to have another function called choose. Where's the function called choose? Okay. But it's not called choose. It's called binomial. Is it? Let's try. And why is it called binomial? Because this thing about choosing yes or no, that's binary, right? And how many, so look at my hand. The word is binomial. Okay, by two, nomial term. You only have two things that you can have, but you're going to select 7 of them. Oh, sorry, out of seven spots, you're going to choose, was it 3 of them? It's either A or B. Okay, so this thing is called choose, but okay, Mathematica doesn't have the word choose because that's a little bit, I don't know, maybe it's a little bit formal. Use binomial. Okay, use the word binomial. So this binomial is very good. Now let's go back to our thing. Okay. Note in Mathematica, you write binomial NK. Okay, so that's good. So let's go back to this thing. Let's go back to this K. Okay, so essentially what you would have, okay, what you would have, if you're going to multiply A plus B 4 times, you're going to have how many? So let's go back to our original question. Oops. It's going to be equal to binomial, right? Right? 4 times A to the power 4. Oops. A to the power 4. Okay. Plus binomial or choose is 4, 3. A to the power 3. B plus, okay, binomial for 2. A to the power 2. B to the power 2. Right? Let's copy that. Okay. 1, 0, B to the power 4. And this is A to the power 1, B to the power 3. Okay. So I've done this calculation 3 times, right? It's as simple as that, but you know, it's very tedious and you know, taking me 10 minutes, like I said. Okay. Right. Well, it turns out this is what a Pascal triangle is. Okay. So, oops. And this is what Pascal triangle is. Okay. Now, let's say Pascal triangle of n. Okay. What's the first line? It's going to be binomial n. One, choose 1. Because that's all I can do. Binomial 2, choose 2. Okay. And then there'll be a space or, okay. Binomial 2, choose 1. And then there's a space, binomial of 2, choose 0. Okay. What else? You're going to keep going. Okay. You're going to have 3, choose 3, 3, choose 2, and then 3, choose 1, bracket, binomial 3, choose 0. Okay. Now it looks like this, but you can, okay. Well, if it's up to n, then it has up to n. I only need 4 actually. In this case, let's make it 4. So basically, just go down to the n, right? And then n choose n choose n minus 1, n choose n minus 2, all the way to n choose 0. Just list that. In this case, I only need 4. Okay. So if I have this, oops, 4, choose 3, 4, choose, sorry guys, takes a little bit of typing. Binomial, 4, choose 1, and then binomial 4, choose 0. Okay. Doesn't look very nice, but look at that. Okay. So now, if you have this on a piece of paper, I ask you, what's a plus b to the power 34? That's going to take you a long time, right? But if you have this table, you can go down to the 34th line, and you're going to have a to the 34. How many terms? 1 term, right? And then you're going to have binomial 34 choose 33. And you're going to have a to the 33 times b, right? A nice pattern is you will always start with 1, because there's only one way you can get everything be the same. And then the second one is always n, because if you only choose 1, you only have n choice, right? So this triangle, when you draw it, and in fact, I have code it, but I spent too much time already. I don't want to find out where it is, but it's in the notebook. You're going to have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and next to 1, you're going to have 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So on the 35th line, you have 34 here, right? It's always 1 less, okay? Now, why does this matter? Why does this matter? This thing, this combinatorial, is one of the things that will define your logic. Because when you have to partition your option, okay, and again, this is going to show up time and again, let's say in decision science or something, okay, how many ways can you sell, how many ways can you assign 3 people to 7 marketing districts? Okay, so anytime you have this kind of combination, okay, obviously if it's small, you can do it by hand. But if it's large, you will see exactly this. Now, sometimes you care about the identity, so you don't divide by that 3 factorial at the end. Okay, it's called partition. Okay, anyway, doesn't matter. Okay, but if you don't care, it's combination. Okay, so the first thing, 210 that I told you about, that one is called partition. It's how many ways you can arrange, 3 students, 7 share. How many ways can I put 3 students? That's 210 ways. Okay, that's partition. How many ways I can arrange? Okay, but in terms of combination of 3 students, and I don't care the identity, I divide that by 6, so I get 35. Okay, so between these 2 formulas, you see it again and again and again. That's why I took this 15 minutes, maybe even more, detour, okay, before we get to calculus. Okay, because it's going to pay off at some point. Anytime you have kind of discrete set assignment, a good word is whenever you look at a problem and there's a word assignment in there. Assignment, okay? Assignment is not like my homework assignment. My homework assignment is I give one homework to everybody. No. This is assigning 3 people to look at 7 market sectors. Okay? I'm assigning 3 colorways to 7 products. Okay? Anytime I do this kind of matching, this or that or this or that, it's always going to come down to this. Okay? Going to come down to this. Now, why does this enter in calculus? Maybe I took a little bit too long. Sorry, guys. So, yeah, maybe I took a little bit too long because I was typing and manually doing this. But in fact, the Mathematica notebook I have has that. In fact, it has a manipulate. But let me let you out with an early break and come back. Okay? Please come back early because we have a lot of stuff to do. My apology, I wasted a bit too much time on this writing thing. Okay? Good. Okay, so I'll see you in about 3 minutes, 5 minutes. Okay. And where's the line? The line. Okay, this is in the line group, right? I'm trying to post. How come it's not in? Can you post this? How come it's not? I just want to post. Yeah, this is the line group, right? It's not ready. Oh, it has out enter. Okay, for those of you who haven't gone out, just copy from the line and draw that. You see that the first index is n. So n could be anything, right? Okay. And the second index just go across. Now k goes up to n. That's why you don't have this, you don't have a square, right? Because if you go down to 7, the first row only has one number. Get up. Okay, welcome back to the second half of today's lecture. Now, given that the first half, again, we took a little bit of time to do the combinatorial thing, and it's a bit of a bonus because it's going to become very useful in analytics much later on. Okay, but I'm just going to use a very tiny piece of information from that, okay, for calculus, basis of calculus. So let's get to calculus proper. Okay, the way to think about calculus, again, is that instead of with matrix algebra, you generalize ax equal to b to just a whole bunch of x, not just one x. Okay, whereas here with calculus, you're trying to find the rate of change to the function b given the change in x. But if it's 3x equal to 13, okay, you always know that every time you increase x by 1, this thing goes up by 3. Well, what if it's not? If it's something more complicated, okay, it's x cubed minus x squared plus log of x. Okay, what's that going to do? Okay, what's that going to do? You can do it 2 ways, right? One way is brute force. Just move x a little bit and measure the difference. But we are going to do something analytical, meaning for a breath of air, for a split, you know, ชั่วขณะจิต for ชั่วขณะจิต time, how much will your car move? So imagine, okay? Imagine. This is a plot of time and this is a plot of distance. Now, you have to imagine that this is on a single road. Okay, single road. What's happening here? Okay, what's happening here? So you start at some point and then you speed up, you accelerate. Okay, so your distance go up. Now, this is not speed. This is a distance, right? So this is how far it goes up. So actually, if you look at this y-axis, okay, if you put the y-axis and you put it down, that's basically the street. Okay, so I start here, I go up to here, I come down a little bit, I go back, so you can reverse, right? Car can reverse. Go up here, come back down, go back up, come back down, and you end up with here. Okay, that's your journey. Okay, okay. Watch my hand. My hand goes up, down, up, down, or right, left. Okay, east, west. Okay, stay a little bit, doesn't move anything, and go back a little bit and stop here. Now, if I'm going to do this and move in time, that's what the graph looks like. So this is actually distance. Okay, this is not speed. This is distance. Okay. What if I want to get the speed? Again, a speed is distance divided by time, right? So if I don't know any calculus, okay, I can say this. At this point, I traveled this far in this much time, right? So that's my speed. However, you will notice, actually, that's not true. That's only average speed. Sometimes I travel faster than that. Okay, I have to go fast and I have to go back up, right? Because if you average 30 miles an hour, and that 30 miles an hour includes you going backward, at some point you must be traveling faster than 35 miles an hour, right? In fact, you don't have to go backward. If sometime during the journey you travel at 25 miles an hour, you know that at some point you have to make up for that by going faster, right? Right? So certainly, if you're going to do this division game, and I send you a little, comment, when do you not need calculus? Well, when do you not need calculus is if you did this. You start here and you go in a straight line, right? And what's the speed? Speed is the slope of that line. Again, if your job is in life is to find out the rate of change in x for equation y equal to 3x, your life is simple. It's 3. And you can take this, divide by this, or this, divide by this, or this, divide by this. Okay? Two things do not matter here. Where you take the slope doesn't matter. How wide is the base of that triangle doesn't matter. Right? Now, in calculus, if you want to know absolutely how fast you were going here, right at this point, okay, at this point, and you don't have like a camera recording the speedometer, okay, but you have this graph, you want to know the slope of that line, okay? So it's not slope anywhere, and it's not slope over a long period of average, 1 second. It's average over ชั่วขณะจิต blink of an eye. So how would you do that? Well, obviously, this is where calculus comes in. If I want to know the slope of this line, what I can do is I can take a straight line and touch it. Right? That's basically what it comes down to. Touch it. Right? And if I do this, then I can do the same thing. I can take width here, height here, I take width here, height here. It doesn't matter where, right? The point is, I don't have that line. Okay? This is only like a way of thinking. Calculus is not done this way. Okay? Calculus is not done this way. Okay? Calculus is not saying, well, to find out how fast the car is, look at another car that's traveling at a constant speed and see which one matches the speed. That's kind of silly, right? Because you can have one that doesn't match. This, you have one that goes slow. So at this point, if you want to know how fast your car is doing, right? You have to take a video cam or something and look at that instantaneous moment, who's moving at the same speed. Yeah, and that's not how it's done. This is only conceptual, guys. In textbook, you see this all the time in calculus, right? But that's only conceptual. You can't really do it in life. How would you do it in life? Well, let's zoom in. Let's draw it a little bit more free, I guess. Okay. How you do it in life? You take this point and you take that point. Again, you can't because it's too far apart. But you certainly can find this, right? Right? Okay. Except you can imagine that this is so tiny, it makes no difference. It's like very zoom in at microscopic level. But the mechanic is here. So what is this time t? And what is this function d? Okay. Now I'm going to switch notation a little. Well, I don't have to. I can. Let me switch notation. Instead of saying distance as a function of time, okay, this thing could be any kind where you are moving. You're moving with respect to making money, right? If you are setting up a shop, right? You set up a shop and you look at the cash register, and that cash register has a number of how much cash in it. Okay, this thing can move up and down. Okay, well, if you're just selling things, it should move up, right? But certainly you can also pay for your supply chain, so it move down. Okay, so how much that cash thing or money in your pocket moves. It's the same thing as the distance over time. So money over time, distance over time, same deal. Exactly same deal. Okay, so how much are you making a month? You can do that as well, right? Tally the beginning of the month, the end of the month, divide by 1 month. But instantaneously, how much are you making? Okay, now in corporate or in finance, that's when it matters. I mean, nobody's going to do like instantaneous much money. Okay, but you can do that for corporate finance, for big company. Same thing. Distance, anything that has a variable. And that variable is time. Right now it's time. Okay, so I move from distance over time to money over time. But time can only go forward. Well, forget about that. I can also have any variable. For example, cost as a function of volume of material. Okay, if you say the volume is 5 cubic meters of concrete, how much is that worth? Okay, you don't have to always add. You can say less. How about less? How about less? Okay, so that can go backward. So there's no special reason why the variable t, now in this case, if it's time, it has to go forward, it has to go backward. But if the variable is a volume, it can go backward as well, right? Right? How much would it cost to have more concrete? How much less would you have to pay for less concrete? Right? And certain things can even go negative. Okay. So obviously, there's no restriction. So because there's no this restriction, I'm going to call this thing F. And this thing I'm going to call X. Okay? Now, what happened here? This is F of X. So I want to know here. This is my spot. So, and I'm sure you've seen this many times. The concept here is, I want to know F of X plus a little bit of distance. Plus a little bit of distance. So I'm going to do this. Escape, delta. There should be a little d here somewhere. Yeah, that's a good one. Okay? But you don't have to. You can use S. You can use any symbol. But I'm doing this to make it look nice. So, back to our picture. This is X. And this is a little bit of X to the right-hand side. So that's called delta. Okay? It's from a Greek word. And we use that to mean change. So, that's what I want. I want slope. Sorry. I want this slope. So I take F at X moved a bit minus X at the point I'm interested in, divide by how much I moved. Okay, so that's it. By definition, this is what I want. Okay, and the whole thing, shift slash, oops, sorry. control backslash delta. Okay. Okay. Now, if I did this, this would be like, delta could be big. So I want delta to be small. I want delta to be small. How do I do that? Limit as delta arrow 0. Literally, that's what I want to do. Okay. Now, right now, if you notice, X is a variable, so it's blue, doesn't know what it is. That's not the real problem. The real problem is I don't know what F is. So if I shift enter, okay, it's just going to give you by the way, this is a nicer way of entering. So maybe I'll put that. Okay. In mathematics, you write this in the limit as delta goes to 0, but in function call, you say limit of what? Right? How as delta goes to 0. So that's what I want. Now let's use let's be a little bit fancy. Let's use our replace, right? Replace. Okay. Now I'm just gonna have one thing. I'm having one thing, something like F go to exponential. Wow. That's not a good example because that's see that? Now I'm replacing with one thing. So if I have more than one thing, I should put in a bracket. I can put bracket as well. Okay. So replace this expression. Sorry. Oh, okay. No, this all. Forget the top. I'll show you later. I'll use that later. What I want to do here is take the value of the function when x is nudged a little bit, minus function at x, divide by how much I'm nudging. And I'm making that nudging smaller and smaller and smaller. Okay, now this is symbolic. Of course, you can't program this in Python or whatever. It has to be symbolic language. I'm going to replace this with certain function. If the function is logarithm, how many of you are not familiar with logarithm? But let's say you all are. And if you've done calculus, maybe you also know that this is the result. I'm going to show you why and how. Why and how. So let's do this first. What if I don't want this? I want function to be cube, right? How do you make cube? Raise to the power 3, right? Now let's be a little bit fancy here. Let's use pure function. Let's use pure function. Hashtag control shift. Oops, sorry. Control hat 3. And to tell you that it's a pure function, I think what happened is sometimes it pays to add a little bit of bracket. Okay, well, I'll come back to this. I'll show you why it's obvious. So let's do this. Let's do this by hand. Yeah? Let's do this by hand. Okay? Now watch this. What if f of x is raising something to the power n? Okay? I'm going to do this by hand, right? Do this by hand. Okay? So this is shift at n. Oops, n. And this is Okay, I think some of you already are smiling as you know what I'm doing. Okay, I want to do this. I want to do this. What does it mean, guys? It means that my distance as a function of x or my money function as a function of x is raised to the power n. Whatever that n is. It's so general, right? So general. The point is that here, I want to find the slope. So I have some function f of x is equal to x to the power of n. At a particular point x, I want to move it a little bit and raise to the power n. Go back to where it is x, raise to the power n. Take the difference, divide by that nudging distance. That's it, right? So if this were power 2, how would it look like? Well, it's going to look more like this, right? Raised to the power 2. Okay. Now, if it's raised to the power 1/2, it's going to look a bit like this. So it doesn't matter. I can use it with anything. Now, for now, and this is a bit of an omission on my part, or most textbook, we are going to assume that n is an integer. Okay, but it will turn out to work with any number. Okay, but n is an integer right now. N is an integer. Now let's look at this, guys. What exactly is that? Come on. It's the same thing we saw in the first half of the class, right? Now let's make it more concrete. Let's make it more concrete. Let's make it 7. Now, what do you think is going to happen? You are definitely, okay? Oops, sorry. You're going to get x to the power 7 plus what? Come on. It's going to be the first one of the Pascal triangle, right? It's going to be what? 6. Okay? And you're going to get what? X to the power 6 times delta. Right? Remember that? Okay, let me show you. Table of 7 binomial. 7 choose k going to 7. Right? Oops, sorry. From 0, not from 1. Okay, see? 1, 7, 21. So what else are you going to have? So say it with me. You're going to have 21, and this becomes 5. And this becomes 2. Right? Okay, can we keep going? 35. 4 and 3. Oops. Right? What else? Okay, let's finish to the end because it's not that many. Okay, let's do 3, 4. Okay. So see if that's correct. Okay. Well, let's expand. Okay. So that's it, right? So I don't feel like typing, so I'm just gonna do that. Okay. So let's do this. So this is what I'm going to get. Right? What do I want to do? The whole thing. Control, divide by delta, right? Right? And I want this to be in here. I want this in there. So in other words, my special function is x to the power 7. Okay. Now, why do I make it a concrete? Because again, I flip back between making concrete example and general definition. So you know that it's the same thing. Okay. Sometimes it gets a little bit hectic. I apologize, but it's actually a very good way to learn. Okay. So what is the slope of x to the power 7 at a point x? It's equal to this, right? You agree with me? Right? So if I want to know how the slope of x to the power 7 at point x, I just say x move a little bit, raise to the power 7, subtract x to the power 7, divide by how much I move a little bit, and make that move small as possible. Go down to 0. Okay? So because of the binomial, by the way, it's a theorem. It's called binomial theorem. You know that when you multiply 7 times like this, the first one is going to be 1. The second one is going to have coefficient, and it's going to be symmetric. You have 1, 7 at the end. Now, this is what mathematicians do. You can't divide, you can't put 0 in here. You can't put 0 in here, right? If you put 0 in here, it goes bad. However, if you have another one on top and they cancel out, it's like, hey, before I put things that is 0 in the bottom, if the 0, this thing here and the top here cancel each other out, right? So I no longer have anything in the bottom that is troublesome. See why the situation is? See this? This guy divide by this, 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 right? Now, I forgot, sorry. There's x. So this is the first, oops. So this is the first term, right? To the power 7, and I have to minus power 7 at the end. Okay. So properly it's this. This is what I want. Oops. Okay. Can you guys see that? Right? So this x plus a notch to the power 7 minus x to the 7. Divide by the notch and make the notch go to 0, making the notch very tiny. Okay, so this is what you should see in your screen. Okay, that's what you want to do. Okay. Now, should I shift enter to see what the result, or let's do it by hand one more time? Let's keep doing by hand. Yeah. So that's that. Well, it turns out, funny enough, because this x7 cancel each other out, right? So this thing goes away. Can you see that? x7. x7. And you get this. Okay. So is that okay now? Is that okay now? Yeah. So I have the thing in front, the back goes away. And now I have this delta on the bottom. Let's cancel this delta with whatever delta on top. It turns out everybody has got delta. Everybody's got delta. So let's do this. So this, take this away. 1, and then this goes away. This becomes delta. And this becomes 2, 2, 1. Oh, sorry. 2. Yeah, 4. And what was this before? 5 becomes 4. 6 becomes 5. And 7 becomes 6, right? Seven becomes 6. Okay? Right? And now you don't need 1 anymore because, hey, that's simple as that, right? Can you do it by hand now? Well, right now you can do it by hand because what? Every time you see delta, it just goes to 0, right? So you get this. That's it. Now, again, oops, sorry. So you get this. Right? Okay, see that? X to the power 7 is nothing more than the binomial coefficient that I spent a long time covering, right? And then subtract that. So it doesn't matter Because you remember, right? If you raise to the power 34, you're going to get 1 over here and get 33 over here. Okay? So the slope of x of n, the slope of x of n is going to be equal to n x to the n minus 1. And that is how you came up with this. Now, obviously, this is a very laborious way of doing things in life. Would you do it by yourself? No. In fact, this is what Mathematica does. It's x to the power, oops. Yeah. Where's that? There's my mouse. X to the power 7, okay, with respect to x. Now, this is what called derivative, okay? The way it's written in Mathematica, sorry, the way it's written in a mathematical notation form, not Mathematica, but mathematical, is this. Well, it's d of x squared. You write it as derivative of x to the power 7, okay, divided by dx. Why? This d here is not a variable. It's shorthand for difference, a tiny difference. That's it. So when you want to do this, so let's say this is equal to limit as x as delta goes to 0 of what? X plus delta to the power 7 minus x to the power 7. And the whole thing divided by delta. Okay. Now, because you know that this thing is gonna cancel with the first thing, you're going to get just one term, right? That has 7 x to the 6 plus and delta. That delta on top cancel with delta on the bottom. So it doesn't matter. So whenever you see something like this, the x to the power n, the x is always going to be equal to n x to the power n minus 1. Okay. And that's the invention of calculus. Okay? That's the invention of calculus. That's like step 1. Okay? And I want you to think about this as pure invention. Now, let's think of innovation. You will learn later on, okay, in the year 1, the difference between invention and innovation. But invention is like something that's a new idea. No human on earth has thought of it. Innovation is when you actually are able to use this to a greater impact. Like it means a lot. So let's say this is an invention. What is the innovation? Innovation is if f is a function of anything, distance, money, price, maybe happiness function, you can always calculate the rate of change. Now, it's not yet an innovation because right now it's very limited, right? It only works for x to the power integer. Okay, so let's take a leap of faith. Leap of faith, but it's not leap of faith. Okay, n needs not be integer. In fact, n can be negative. Okay, it can be negative, right? So for n positive integer, need not be integer, needs not be positive. Okay, it can't be 0 because if it's 0, it's a constant. There's no difference. constant is 0. Okay. So that's the only leap of faith I asked because it works. And then we can have other leap of faith, like if I have derivative of f of x dx, okay, and I have plus g of x. So leap of faith. Okay. This thing will be the same thing as take individual derivative okay, separately. Okay, so this is a leap of faith. Okay, derivative of two functions add together is equal to derivative of one function add to another derivative of function. Well, that's kind of obvious, isn't it? Right? If you have a function that accumulates money, the rate of change of making money over time is the derivative. But if you own two businesses, this one has its rate of accumulating business, right? Accumulating profit. But because you own both companies, right? The rate that you accumulate profit from two companies is the same thing as the rate of accumulation from this company plus the rate of accumulation from this company. Okay? Now, speed, it's the same way. If you have the rate of change of you moving, walking, and you have the rate of change of, in the airport, you have this belt that moves, right? So if you are walking on top of this belt, the rate of change in total is a sum of your speed relative to the belt plus your speed relative to the, plus the speed of the belt relative to the wall. Okay? Now, when would this not be true? I'm just asking you a funny question. When would this not be true? If the speed of belt goes fast enough, approach the speed of light, then Einstein said no go. Okay, then it becomes more complicated. You don't add. Okay, but for ordinary thing you do. Okay, so that's that's not why Einstein won the Nobel Prize. He won Nobel Prize for something else. But that's one of the things that he published in 1905. Okay, so what else do you need to do? Now there's another rule. Okay, now this is tricky. I'm just gonna write d of f of g of x. Uh-oh, that's a scary thing. Now, how many people look at this and think it's scary? How many people look at this and think, wait a minute, that's nothing more than calculate g of x, scramble the egg, and put it in fried rice. So g of x become variable y and f of y, basically. So this is a shorthand for f of g of x is a shorthand for f of y, where y is g of x. Okay, so in this case, now I'm just going to write, okay, and it looks like a leap of faith now because it can be proven, obviously. It's going to be equal to d of f dy times d of y times dx, where y equal to f of x. Okay? So it's like I take this company, okay, from the raw material, okay, I multiply by 3. And then from whatever I get, I multiply by 2. So it's 3 times 2. So it's sort of like double it's not double, it's take the product of the first operation, put in the second operation, do something to it. So the rate of change with respect to raw material is the rate of change with respect to the intermediate product times rate of change of intermediate product to the raw egg. Okay? So that's why you get this multiplication. This is called chain rule. Now, these are not really leap of faith. In your mathematics 101 class, you go in detail, okay? But you don't need more intuition than that. The idea is that with this, now, what else remains? You have the recipe for taking the derivative of x to the power n. You have the recipe for taking the derivative of x to the power n plus x to the power k. You have the derivative of y to the power n, where y is equal to x to the power k. Right? What else you don't? What do you not have? Function that is not x to the power n. Right? So now leave it to other. Okay, derivative of special function of x. Well, it's not really special function, but it's not the power. Okay, so I'm gonna say derivative of h of x dx when h of x is not x to the power n. Okay, so this becomes a little recipe like souffle or something. Okay, so these are, so you have one recipe. So this is the first recipe you have. Okay, whenever you have a function that is x to the power n, its slope or rate of change is n times x to the n minus 1. I tell you that this recipe is so good, n can be 7.2. And this is going to work. Okay, it's going to be work. Now, it's not going to use the binomial theorem. It's going to be more general than that, I guess, to say in a manner of speaking. Okay, so you take this thing, you take a leap of faith that it can be this. And you can also add, okay, this. Now, and this for a whole bunch of h function. Okay, in other words, there's so many of them. For example, e.g., h of x is equal to exponential x. I'm going to put in mathematical notation so you know. Okay, or sine of x, right? Cool. Okay, tangent hyperbolic x. Okay, so this is something you can play with. Okay, now you're not expected to know this because these are sort of like specialist recipe. Okay, so how would you know it? Well, you go to Mathematica and say, okay, I don't know what the special formula for this is, so let's do that. So let's say my special function is tangent h of x. You don't have to know what it is. Gives you another function. Okay, now this are sort of like quote unquote memory formula. Okay, but you know, the point is you done enough, you kind of, okay. So these are all the things. So how would I, let me do this. Let me say, let's do this. Let's make it a pure function. Derivative of anything, make it a pure function and apply it to a list of sine, cosine, log, exponential. What else you got? Interesting function? Okay, tan, and okay. See, these are all the derivatives. Now, obviously, when you're an engineer, you work with this so much that you're gonna memorize it. Okay. In our world, chances are you only need this guy that you have to memorize. So basically, exponential is a derivative of itself. Okay. Let me show you this. Derivative of exponential x is equal to exponential of x. True. That's why you hear this word called exponential growth. The bigger you are, the faster you grow. Because the speed in which you change is the same thing as your size. This is your size, guys. This is how big you are to begin with. Okay? And this is how fast you grow. How fast you grow is exactly the same value as of how big you are. So if you're small, you grow small. If you're big, you grow large. That's why you have this thing called exponential growth. The bigger you are, the faster you grow. And that is the mantra of startup. You want to be on that part. Now, let me tell you this. In life, because exponential function goes to infinity, nobody goes to infinity. What that means is a startup is at that phase of the business where the slope is so increasing so quickly that the bigger you are, the faster you grow. At some point, this will stop. At some point, this will stop, okay? So nobody has permanent exponential growth. Same thing with your population. Right now, human beings, humanities is experiencing exponential growth in population. At some point, we're going to start peaking. Okay? China is already having this thing. It has to be natural thing. By the way, you will hear semi-intelligent people say this all the time. Thailand is an aging society. China is an aging society. So we don't have enough children to take care of our elders. So what do? We should have more children. That is stupid. Okay? You don't solve demographic problem of aging population by having more children, because that's just going to postpone your problem down the line. Okay? The solution is to say, how can this many old people with this many people, young people, look after this many old people? And that's why you guys have health and well-being. Smart city, inclusive society, sustainable development. All these three things very much touch on the fact that Thailand is an aging society. And soon, every country is going to be an aging society. At some point, it has to be, guys. It can't be. Rome was like that. India hasn't gotten there yet. China is already getting there. China is kind of like this now. India is still doing this. The world is still doing this. But at some point, Thailand is already doing this. So Thailand, China, okay? So aging society is not solved by having more children. It's just going to make things even worse, bigger problem down the line. At some point, you have to manage it. Okay, but anyway, the point is that initial rise is the exponential function. So when they say, oh, we want Basai to be innovative, create new business, and be on the exponential, that is only a temporary situation. If your business caught on, if your business doesn't catch on, you don't make any money. But even if your business catch on, you are going to experience a short period of exponential growth. It happens that way. Usually, if you're selling something that's not new, like everybody has a noodle shop, you're creating a noodle shop, then your growth will be kind of linear. But if everybody has a noodle shop and you invented spaghetti, okay, you're going to have exponential growth. Until at some point, spaghetti no longer grows exponentially. Okay? So innovation works that way. Okay. Now, so if this were what I want you to do, okay, is pretend again. Now start to pretend. I already showed you the page of demonstration, right? When you go to that demonstration page and you download, okay, there are two downloads. There's one that says download. You're just going to download what's called CDF, and that's for like public. Now, you are better than that because you want the source code. You go to a little bit to the right, it says more, and download the source code. Now, for this one, this is your source code. Okay. I just want to touch a little bit here. I'll do more of this on Wednesday, but I want you to get ahead because now you can start doing something here. This is how demonstration projects are formatted. Okay, it's like a rule. If you're going to submit demonstration, you can't just throw in a code, see that it works. You have to write explanation. You have to do this and that. Okay, so I had to do the same thing when I submitted my thing. So it's kind of like a template. It's a good manner kind of. So the format is you have this thing called initialization code. That means before you get to the main problem, you have to do something. So if you double click, you see that, oh, it creates this function. Now, what this function does is called integration. Integration is the opposite of differentiation. Okay, so a lot of time when you take calculus 101, and you will start with what's called differential calculus. So taking the derivative slope, the slope is derived from the function. That's why the word is derivative. So if you have the distance function, take the derivative, you get the speed. Integration is the opposite. It's saying, what if you have the speed plot? Can I go back to distance function? It's kind of like going the other way around. Okay? Same thing with money. If you keep making more money, you can ask in differential calculus, how much more money per instant of time? Conversely, if you have that function, you can say, how much money am I accumulating over a month? That's called integration. Integration, Basai School of Integration, that's integrating many knowledge. In this case, they're not integrating many things. They're just integrating more of the same thing. So when I integrate the profit function, I am integrating profit from yesterday with profit today with profit 2 days ago, adding. So integration in this case means adding. Okay, anyway, so I'm going to show this at the beginning of Wednesday. Okay, the point is, when you work with demonstration program, everything is going to end up with manipulate, because that's what tweaking is. It's the whole thing about interactive, right? But here's the thing. You can copy this. The author makes this available. He wants this thing to be copied. Okay? This is not like you're stealing things. They want you to share this. They want you to use this. So what you do is go down here, and that's the code. Now, the code is going to look messy. Okay? The reason it's going to look messy is because when you're trying to do many things, like adjust the font, make it to the center, blah, 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 you have to add this specific command. Okay? And that command, if you write in many lines, it's going to look long. They want to write something very compact, so they squeeze everything in one line. So in one line, draw the plot, make sure the left-hand side is yellow and the right-hand side is blue, and the size is 7 by 7, and there's a heading. So it's really messy, it's difficult to read. But here's your weapon. You have already done some manipulation. So you know at some point there's going to be an action. Well, first of all, you know there's going to be some variable definition, usually in module. Okay? Maybe not, but usually in module. That's definition of the variable. In this case, this guy also has a definition of function. Fine. So these are all the definition. Then in manipulate, at some point, there's going to be a visualization. That's the whole point, right? And then this function is going to depend on parameter that you can tweak. So there's going to be a control section at the bottom. So all you need to realize first is that, that's my visualization function, show. So this can be complicated. It can be show, graphic, can be plot 3D, surface plot, histogram, can be all kinds of stuff. But you know that's the action. That action is always going to be producing some kind of picture. And here, it has all kinds of things. In this case, these are the knobs, right? What are the knobs? In this case, the knob, if you look here, is not value, but choice of function to display. And they have, right now, how many choice of function? 1, 2, right? So if you shift enter, you're going to get this. And you play with it first. Yeah, first thing you do, don't go in the code. Sorry, my bad. First thing you do is play it. Okay, so there it is. Now, this function will introduce you the concept of the opposite. You have a blue line, I think, if I'm not mistaken, the blue line is the speed. And the orange area, sorry. The orange area is the speed, and the orange is the speed, and the blue is the accumulation. So this is going to teach you the second part, which is integral calculus. I'm going to start on Wednesday. Why? Okay, well, and this just gives you that. But you will notice that these are the choice of function. Now, the difference here is that back then you didn't have this arrow thing. This is kind of cosmetic. If I put in x squared divided by 10 like this, it doesn't look nice. So what the guy does is to say, show it in traditional form. Okay. So right now, if I click this, it's okay. So if the speed is x squared, the distance is going to be, well, it's actually going to be x cubed somehow. Okay, but I'll show you the opposite. But you can already see that, right? If the distance is cubed to the power 3, the speed will be squared. So it obviously makes sense. If the distance is squared, the speed will be, so if the speed is squared, the distance will be cubed, right? Now, what if you want to play with it? And this is how you get into, not hacking, but this is the purpose. I want to try something else. Okay, I don't want x squared. I want x to the power 7. So, yeah, so you can go that. This is how they. So this is we did the 7, right? Now this is just a starting point. So I can. Yeah. See why it's messy? Because in one line the guy is saying that start here with the size 14 and make it purple. All this is, you know, not necessarily. So let me just do this. Clean it up a little bit. Oops. Yeah. There. See? The first function is now x to the 7. So imagine that. Yeah. Well, you don't care now. You don't like x7. So let's take a log of x7. Yeah. How about that? This is what you want. So put that in here. Again. Okay. See? So that's your function. Now your function will look different. So now you can play with anything. Okay, now you can play with anything. How is this powerful? Well, you don't have to learn, you don't have to self-study integral calculus because I'm going to teach you on Wednesday morning. Okay, but imagine this is another concept. Okay, and you don't have me. Okay, you don't have me. Okay, now I'm teaching you integral calculus Wednesday morning. Fine. But if you don't have me, you don't have Wednesday morning, you've never taken calculus, you want to learn about integral calculus, you can play with this. Okay? The point is that, well, for this is for high school students who are learning calculus. But you can be learning about something else. Data analytics, right? Drawing function, all kind of stuff. Biomedical engineering, drawing molecule, putting a chemical bond together, in which case you would just go to demonstration page here and look at the concept of your choice. Okay. Again, here you're looking at concept of integral calculus, which you don't need to because on Wednesday morning I'm going to talk about it. Okay. Now, but if I didn't talk about it and this is something else, some other concept, you can learn by yourself. Okay, let's say, and this is true, by the way, when COVID came out, there's a model for how, if you take measurement of how many people and it's going to grow up, there's a way of modeling it. I want to learn how to model it. Okay, so I looked up. Now, I know the theory, it's called SIRD, blah, blah, blah. But I want to look at the implementation, play with the parameter. So what do? I go to demonstration project. I search for something called spread of disease. So I look at it. I know how it works. Now I want to add in my own flavor. Because the way the model works is just initial rate of contagion till people die or whatever. But I want to say, well, what if the government intervened and start requiring people to wear masks? In which case, the beginning rate of infection has to be sort of tempered. So the rate can be tweaked down a little bit. If you would want to put that parameter in there, how would you do it? The demonstration program doesn't have it. So once I studied it, I added it, right? So if you go to my YouTube, there's a subdirectory that has to do with COVID modeling. And that shows my own implementation of COVID spread model. Now, I have to tell you that COVID spread model only works for one shot. In other words, initial rate of this, and then, but once you have the second wave, all bets are off. So I maintain that my model is very accurate. You can calibrate my model to be very accurate for the first wave. But once you get to the second wave, you can't use this model anymore. It's a different thing. You can use it again, but then recalibrate. So anyway, how did I do that? Well, I could read purely the mathematics or biological textbook and program it, but that would have taken me a long time. So my shortcut was, I know this is a theory. My bet is, hey, somebody in the Mathematica community already showed it. So I searched. Sure enough, somebody already did it. But he had a basic model. I want to tweak it up, jazz it up with my own version based on this. So I took part of it by going through this and then added my own flavor. That's exactly how you can keep your innovation. You know, because your innovation, you're not just going to extend some guy. It could be something, example would be something like this. You're doing marketing model, but you notice that in your marketing, there's a contagion effect. Maybe some kind of influencer effect, or maybe some kind of word of mouth. So you think, hey, wait a minute. If I'm introducing a new product to a market, that's almost like introducing a new virus to a community. Can I do that? This would be innovation. Okay? This is what we mean by multidisciplinary. Because, hey, you're taking a model from biology. This is done by biologists, guys. It's not done by you and me. Developed maybe by a mathematician who's married to a biologist. I don't know. Okay? Or maybe a biologist who's married, who had a strong calculus background, because these things calculus. So they develop it, put it out there. You look at it, again, because you're not narrow-minded. I'm just going to sell things. I'm just going to sell things. I'm just going to sell things. So you do marketing. When you look around and say, hey, there's a biological model driven by mathematics that works for my market. Why don't I use that? And that would be like written a page. When they were ranking the Google and they look at the mathematics and they beat everybody. They kill all the search engines. You know, they're the only search engine standing by the end of whatever, 2000. Okay? That's what I want you guys to do, right? Okay? Chances are you will not be creating new model of how disease spread. That would be the breakthrough in biology. But the ability to say, hey, wait a minute, that same kind of thing, maybe works with my marketing strategy. Okay? Now, if you want to do that, it's no longer an innovation because that's called viral marketing. Viral marketing operates exactly on the same mathematical equation. Although they may not say, viral marketing means you spread your idea as a contagion. Right? So TikTok market, that's what I think. That's from this. So if you're gonna use that as your innovation, I think you're a bit late. But you see what I mean? People who invented viral marketing, they're not brilliant marketers. They're not brilliant biologists, epidemiologists. Use the right word. People who study the spread of disease, but they know how to say marketing plus virology, virus spreading with mathematics. So there's already a multidisciplinary when some biologists apply mathematics, and then there's another layer of of multidisciplinary where the marketer looked at the biology model that's driven by mathematics applied to their marketing strategy. Okay, so the whole thing is a long arc, guys. Okay, the mechanics of it, I'm not so worried because your first year you're going to learn how to take differentiation, all kind of stuff. I want you to think. Okay, so on Wednesday, I'll come with integral calculus. Now, once you've got integral calculus, I'm going to jump to probability. The reason I put probability last is that the most powerful concept of probability is that of probability function. So instead of likelihood of some event, you think of likelihood of some event as a function of something. And then the total likelihood will be integration of likelihood over a range of that something. Okay, again, I'm right here. What's the probability that I see a girl? That's a probability. And I keep moving. 2 row, 3 row, 4 row, 5 row. So what's the probability of me seeing a girl right now? It's actually an integration of probability of a girl in the first row, second row, third row. Now, if I did this in a continuous way, it's an integration function. So there's a function of likelihood of getting to see a girl or someone with glasses or one with short hair over number of people. And I just keep adding more people. So over this range, I have 0.3 probability of seeing a girl, 0.4 probability of seeing somebody with glasses. So calculus is fundamental to probability. And in life, if you don't have probability, you can't do any kind of analytics. Okay? My last word for today is all the fancy schmancy things you see about data analytics, machine learning, AI, all stuff, 99% of it is about producing your estimate of a probability of something. That's what it comes down to, guys. Okay, so probability will be the climax of our time together here, and that is going to be doable after I talk about integral calculus. Okay, meanwhile, go play with this thing that I sent you. Okay, and maybe you can read a little bit of my essay about when to need calculus. Okay, but again, I don't want to just be you to be able to mechanically do things, because like I said, you have this powerful engine for you. But think, okay? So you should, when you go home tonight, you tell your parents, I know how to take the derivative of x to the power 7. Your parents are going to say, oh my God, I knew that when I was a baby. Okay, that's not the point, right? You have to know exactly why x to the power 7, take derivative, you get 7x to the power 6. Okay, look at that. Okay, I think so I'm sorry, I ran out over time. My bad. Hope you don't mind, just a little bit hungry. Okay, I'll see you on Wednesday. Okay, see you on Wednesday.